Imagine a telescope so powerful it can peer back in time to the early days of the universe. This isn't science fiction. It's the James Webb Space Telescope, or JWST. Launched on Christmas Day 2021, JWST is the most advanced space observatory ever built. It's a marvel of human ingenuity and a testament to our unquenchable curiosity about the cosmos. JWST is named after James E. Webb, the NASA administrator who led the Apollo program. Unlike the Apollo missions, JWST takes us to the edge of the observable universe. It's designed to capture light from the first galaxies that formed after the Big Bang. This light has been traveling for over 13 billion years. JWST is our time machine, allowing us to witness the infancy of our universe. With its massive 6.5-meter mirror and advanced instruments, JWST can detect the faintest signals from the most distant celestial objects. It's like giving astronomers a pair of superhero goggles to see the unseeable. JWST can peer through cosmic dust clouds, study the atmospheres of distant planets, and even look for signs of life. JWST is more than a telescope. It's a bridge between what we know and what we dream of knowing about our vast, mysterious universe. For decades, the Hubble Space Telescope has been our premier eye in the sky. It's shown us breathtaking images of nebulae, galaxies, and planets. Hubble has been a faithful cosmic companion orbiting Earth since 1990. But as remarkable as Hubble is, JWST is in a league of its own. It's like comparing a smartphone camera to a professional DSLR. JWST's primary mirror is 6.5 meters in diameter, nearly 3 times larger than Hubble's. This means JWST can collect much more light, allowing it to see fainter, more distant objects. JWST operates primarily in the infrared part of the spectrum, while Hubble mostly uses visible light. This is crucial because infrared light can penetrate cosmic dust clouds that block visible light. JWST can see through the cosmic fog that Hubble can't penetrate. Another key difference is their orbits. Hubble orbits relatively close to Earth, about 540 kilometers up. JWST, on the other hand, is much farther away, about 1.5 million kilometers from Earth. This distance allows JWST to maintain a stable temperature and avoid interference from Earth's heat and light. It's like moving to a quiet countryside to stargaze, away from the city's light pollution. JWST's superpower is its ability to see infrared light. Infrared is a type of light that's invisible to our eyes. It has longer wavelengths than visible light. We often associate it with heat, but it's much more than that. In astronomy, infrared light is a key to unlocking cosmic mysteries. Many celestial objects emit most of their light in the infrared spectrum. This includes cool stars, distant galaxies, and planet-forming disks around young stars. By focusing on infrared light, JWST can study these objects in unprecedented detail. One of JWST's most exciting capabilities is its ability to analyze the atmospheres of exoplanets. When an exoplanet passes in front of its star, some of the star's light filters through the planet's atmosphere. Different gases in the atmosphere absorb different wavelengths of light. By studying this filtered light, JWST can determine what gases are present in the exoplanet's atmosphere. JWST's infrared vision also allows it to peer through cosmic dust clouds. This means JWST can study star formation, observe the centers of galaxies, and even look back to the early universe when the first stars and galaxies were forming. JWST's home in space is as fascinating as the telescope itself. It orbits the Sun at a special location called the second Lagrange point, or L2. This spot is about 1.5 million kilometers from Earth, in the direction opposite the Sun. At L2, the gravitational pulls of the Sun and Earth combine to match the centripetal force needed for an object to move with them. This creates a relatively stable position in space. For JWST, this stability is crucial. It allows the telescope to maintain its position with minimal use of fuel. At this location, JWST can keep the Sun, Earth, and Moon all on the same side of its sunshield. JWST needs to stay extremely cold to detect faint infrared signals. The sunshield blocks heat and light from these bodies, allowing the telescope's instruments to cool to nearly -233 degrees Celsius. The L2 orbit also provides JWST with an unobstructed view of the universe. Unlike Hubble, which is often blocked by Earth as it orbits our planet, JWST has a constant view of the cosmos. This means more efficient observing time and the ability to conduct long, uninterrupted observations. Section 5. Crystal clear, JWST's advanced imaging technology. At the heart of JWST's incredible capabilities are its advanced imaging technologies. The telescope's primary mirror is a technological marvel in itself. It consists of 18 hexagonal segments made of beryllium and coated with a thin layer of gold. These segments can be adjusted individually to focus light with extreme precision. JWST's instruments are designed to capture and analyze light with unprecedented sensitivity. The near-infrared camera, or NIRCam, is JWST's primary imager. It can detect light from the earliest stars and galaxies. The near-infrared spectrograph, or NIRSpec, can observe up to 100 objects simultaneously. One of JWST's most innovative features is its coronagraph. This device blocks out the bright light of a star, allowing the telescope to see fainter objects nearby, like planets or dust disks. Another groundbreaking technology on JWST is its microshutter array. This is a grid of tiny shutters, each about the width of a human hair. These shutters can be opened or closed individually, allowing JWST to study multiple objects in a single field of view while blocking out unwanted light. Section 6. Unveiling distant worlds. The search for exoplanets. One of the most exciting prospects of JWST is its potential to revolutionize our understanding of exoplanets. These are planets orbiting stars other than our Sun. In the past few decades, we've discovered thousands of exoplanets, but JWST will take our exploration to a whole new level. JWST's infrared capabilities are particularly suited for exoplanet research. Many exoplanets are too faint to see directly in visible light, but in infrared, they shine brighter relative to their host stars. This makes them easier to detect and study. JWST can even analyze the atmospheres of some exoplanets. One of the most tantalizing possibilities is the search for biosignatures, chemical signs of life, in exoplanet atmospheres. JWST can detect gases like methane, carbon dioxide, and even water vapor. These could be indicators of life as we know it. JWST will also help us understand how planets form and evolve. By studying the disks of gas and dust around young stars, we can learn about the birth of planets. Section 7. Peering into the past, exploring cosmic origins. JWST's most awe-inspiring capability is looking back in time. Light from distant objects takes time to reach us. The farther away an object is, the older the light when it arrives. JWST detects light traveling for almost the entire history of the universe. It observes the universe just a few 100 million years after the Big Bang. We'll see the first galaxies forming and the universe transitioning from darkness to light. JWST helps us understand the universe's evolution from its early state to today. Section 8. Engineering marvel, JWST's innovative design. The James Webb Space Telescope is an engineering masterpiece. Its design pushes the boundaries of space technology. The primary mirror is 6.5 meters in diameter but had to fit inside a rocket. The solution? A folding mirror. 18 hexagonal segments unfolded in space. Then there's the sunshield. This 5-layer structure is the size of a tennis court. It protects the telescope's instruments from heat and light. Each layer is as thin as a human hair, made of captain. The sunshield keeps the instruments at -233 degrees Celsius. JWST's instruments are marvels in themselves. The near-infrared spectrograph uses a microshutter array. It can observe up to 100 objects simultaneously. JWST maintains its position at the L2 Lagrange point with precision. Section 9. The deployment dance. JWST's journey to full operation. The launch of JWST was just the beginning of its journey. The process of deploying the telescope in space was a complex, multi-step operation that took about 2 weeks. It was often described as the most complex deployment sequence ever attempted in space. Each step had to be executed perfectly, with no room for error. The deployment began with the unfolding of the solar array, which provides power to the telescope. Next came the deployment of the communication antenna, allowing JWST to stay in touch with Earth. Then came one of the most critical and nerve-wracking parts, the unfolding of the massive sunshield. This tennis court-sized structure had to unfurl without tangling or tearing. After the sunshield was in place, it was time for the mirror to unfold. The 2 side panels of the primary mirror, each holding 3 mirror segments, had to swing into place like the wings of a butterfly. Then each of the 18 mirror segments had to be precisely aligned. Finally, JWST had to cool down to its operating temperature.